Well, good morning. It's great to be in London again after many years. I should say lovely. It's good to see old friends. I don't know where Jakub is, meet some new ones. So my goal here today is to talk about, kind of share how we think at Temporal about building reliable applications. What do you mean by reliability? And this is like the fair question, what does it mean? It's a business question. It's a question what kind of measures we want to take to achieve real or sometimes perceived reliability of our business so that we can continue running our business. And these measures, they have cost, right? That's the development cost, operational cost, but also opportunity cost. And so let's start with a very simple case. If I run something non-critical application, like usually did my mic die? Oh, good. Thank you. If I write something like stateless, like for example, it's a cache service or maybe traffic routing or CDN, I can afford to lose my state. I can afford to lose this instance because I can always start it somewhere else. And so that's why I'm thinking about this analogy with the three little pigs fable. If this is a kind of straw house, then a hungry wolf will come and huff and puff and blow away my house, that's fine. I can run away and build a new one quickly because it's a stateless system, right? But most applications, they have state, right? They have some data that you don't want to lose. Because stateless, I could have run in the basement of my house. I can run it anywhere. I can run in the data center. But for stateful, I don't want to lose my data if a machine dies. And physical machines die, hard drives die. And usually, like, we go to the cloud. We can use like NAS and the SAN solutions, but these days, usually we go for like AWS EBS or Azure Managed Disk, so that whatever happens to our machine, our data isn't lost. And this is durability, which is most important aspect of reliability, that the data isn't lost. But what about reliability? So let's say it's a database server. I want to use like database as a kind of simple example, but of course, real systems are much more complex than that. So like data is safe, but if our server crashes, we still need time to recover, restart, deploy new instances, configure them, run them. And that may be fine, right? So it's again, a trade-off. Can we afford that kind of risk in the business? Can we be down for, I don't know, a few minutes, a few hours? And it may be totally fine for our business. I still see like periodically this financial, like the bank websites that have this banner on Saturday morning, oh, sorry, we're down for maintenance, come back later. Which is kind of surprising in the 21st century, but they consider that's fine for them. They don't need to build anything bigger than that. So it's application specific. Now, if that's not enough, if they want to be down, if we want to be always up, we need something bigger. We need to build like a brick house as opposed to like a wood stick house that our hungry wolf would not blow away. And so we go for either like in-house solutions if we self-host, or again, these days we go for like managed hosted services, like AWS RDS. They run this database. They run multiple instances. They do replication. They ensure that any kind of dying physical machine will not bring the whole system down. So we can pay, that costs money. But again, if for our business, if that's important, that's money well spent, right? So this kind of, we get to this reliability when a single domain, like a single, like a AWS region or other cloud providers region. But then when I was reading this fable of three little pigs, like back in the days in my childhood, I was always like thinking, this wolf must be stupid, right? So it decided to break into the brick house through the chimney. Like instead, he just waited outside and just lay siege and wait for the pigs to come out because they will have to come out. So this kind of doesn't make sense. And I think that if you, as a child, think like that, you're kind of destined to become an engineer. You question the system reliability. But then, on the other hand, if you think, why are these pigs not a kind of in the safety of a farm? You're probably a software manager by now, an engineering manager by now. But then, if I were to write this fable today, I would call it, oh, it's kind of a strange slide. I would call it oh, the slides have made it. Okay, anyway, I would call it the four little pigs. Because the fourth pig would be the most forward-thinking, the smartest one. It would build not just one house, but two. We connect them with the tunnel. And ideally, it would be like the river and mountains and the forest so that the wolf could not cross, would not see what's going on, because our pig would just run away and go to the other house and continue operating there. Kind of, the pig would go for like geo-redundancy, probably called like Lampert pig. Although Lampert would probably require 3 houses and 3 tunnels at the minimum. But you see the point that when the risk is high, when the pig is afraid of being eaten, then it's worth investing in a system, like geo-redundant setup, where I can just go and recover and be fine. But if the risk was different, if it was just maybe a tree fallen in case of the windstorm, that's okay. It can damage the roof and go and repair. We don't need to pay for this elaborate setup. So again, I want to stress that this is a business kind of decision with which solution to go. Now we got redundant. We solved one problem, but of course we created 2 more. This is always in software. So the main problem here is consistency. How do we guarantee that both systems get the exact same state, whether we're doing accounting or any kind of other data? So there are really 2 approaches to this. We can do synchronous replication or asynchronous replication. And synchronous is conceptually very simple. In terms of when we update something, when there is an update to the state, we don't acknowledge update until we write it to both sides of both systems. And so it's very easy to deal with. It's like very simple, but there are 2 downsides to it. One is its availability, because now for that write to be successful, we need both systems to be up. And any kind of issues, any outage of either of the system makes our system unavailable. So it's kind of ironic that we went for this setup for high availability, but actually got reduced availability. So the availability mathematically of these 2 systems together is less than of each one of them. And of course, there are like other solutions. There are quorum-based algorithms where you need like 3 replicas. But 3 is also very dangerous, because if you're trying to write to 3 and got acknowledged, write acknowledged by 2, if one write fail, we're in a very dangerous state, because any of the other replicas, if we miss it, we'll lose the write. And so we need to quickly repair. And if you attended yesterday talk by Datadog folks, I think they ran into exactly this problem, where all these quorum writes were acknowledged, but they discovered later they lost data. Very typical situation, very, very dangerous. And then if you need to repair, you need to scan the whole database, whole table. That creates pressure performance-wise. You run into tombstones, so nothing is free. And then you need to go with like more replicas, like maybe 5. And imagine you deploy to 5 regions just to kind of survive. And in terms of a cap theorem, what we built is they call the CP system. We sacrifice availability for consistency. Our consistency is strong. Data is available in both places, but we are less available than otherwise. And that kind of applies no matter where in the stack we do it. We can do it at the application layer, we can do it at the database, the storage layer. It's the same kind of consideration. Now, if you go with asynchronous replication, we acknowledge writes when we get it to the primary. So primary writes the update, and we acknowledge right away that it's done. And then we asynchronously send this data through some kind of version of log shipping to the secondary. And then eventually gets written there. There is some delay, and that's why it's eventually consistent. If we fail over before data writes, we may be in kind of inconsistent state. And this is in CAP terminology in AP system, where we sacrifice some consistency. We went for eventual consistency for high availability. But in this case, availability of a single replica is always higher. And then something happens, we fail over, and again, we get high availability of the other replica. The other factor that's important to consider here, we don't sacrifice latency. So the system, we always try to talk to our local replica, and we only do like round trips to this one like primary. In synchronous case, we have to talk to both replicas, and if they're in different regions, so like tens of milliseconds of round trip, especially if we run some complex two-phase commit protocols or like Paxos, Cassandra lightweight transactions with 5 round trips, the latency cost of doing synchronous replication is pretty high. And so asynchronous, again, like the same consideration about AP versus ACP system, it applies no matter like which layer of a stack we do it. So we go, like at Temporal, we believe AP is better because most people prefer availability over consistency. And so like, how do we deal with potential inconsistencies? It's not like you always get it or frequently. It may happen occasionally when you fail over and something like that. But application logic doesn't like inconsistencies. Some invariance in the application state may be violated. The application may crash if it reads data that's kind of out of order. And so there are known tricks and techniques in our industry. Like one of them is event sourcing. So instead of updating state of a particular entity, we kind of maintain a log, append on the log of all updates to it, like, in this case, like habits and credits. But anyway, any update that we make to a particular entity, we append it, and it's immutable records. And the final state of the state is always calculated on the fly based on the history of these updates. And so this event sourcing is kind of compatible with asynchronous replication, because we can have some events already replicated, and some may be in the pipeline in flight. And the software that uses event sourcing, it expects it. It expects that new events may arrive, and then I recompute my derivative aggregates. The other technique is idempotency, and I would say that sort of internet is based on idempotency. If the idempotency wasn't used, everything would be collapsing. The idea, as we all know, is simple. Any operation with the side effects, we assign a unique ID. So we make a call to some API, we pass this idempotency ID so that in case we retry it later with the same ID, it would not execute the same operation twice. Like it will not double charge, for example. So these are kind of two techniques, very, very popular, very known. And so when we go to temporal, what does it mean for temporal? Temporal architecturally is built essentially on event sourcing. Like all these workflows that run, they have their append-only log of their event history. So this kind of all in the core of the system. And all activities, they expect it to be idempotent. That's a requirement. That's a must. One of the kind of must-have rule that all activities are important. And because when you execute temporal application, workers may restart, or some workflow that was sleeping for like several days got a signal and it gets resurrected, replayed on the worker. It needs to go to the history and reapply all the history events. And that's why these requirements are tested over and over again. That's kind of at the very basis of the programming model. And that makes temporal programming model a very good candidate for asynchronous replication, because we have whatever, like 26 to 28 events, and we replicated a subset of them. The system expects that new events can be added, and that's okay. That's kind of in the model itself. But on top of that, there's a requirement for determinism overflow execution, so that if you run the same code, it expects to produce the same exact results. So even if we receive not all events, like for example, if we do like hard failover and say lost some of the events, in most cases, in many cases, we can generate these events anyway because of the determinism of the workflow logic. There are caveats for things like events and some kind of external data, but generally the system, the programming model is very resilient, very well suited for asynchronous replication. And so it's the same kind of AP system. We go for eventual consistency, but I'd say in temporal case, it's kind of like a stronger flavor of eventual consistency because of this requirement for determining the workflow code. We announced our GA of replicated namespaces, where if I go to UI and have a namespace and I add a second region, that immediately starts replication to another region for the same namespace. And then once a replication completes, once we have the state synchronized, we can fail over, and then the replication goes the opposite direction from what used to be passive or secondary now became active. So it becomes source of replication the opposite direction. So this is where this tool allows us to make this very simple. Allows this system look very simple, where this replication happens because of the properties of the system. And it's a very critical tool, and we use this replication for years. Internally, before we introduce replicated namespace, we use it internally for moving workloads around. Because we run these multiple clusters in the region, and sometimes we need to rebalance the load. Sometimes we want to replace this cluster called cells. And instead of applying some dangerous updates in place, we create a new cluster, then we migrate all namespaces from the old one to the new one and shut down the old one, because it's a safer way of doing some dangerous updates. And so we've been doing it for many years, and that's when making replicated namespaces was some effort, but it's on a very solid foundation, already tested for years of running it. Liang talked yesterday about migration from on-prem to cloud and back. It's also exact same stack, exact same replication stack, but it allows us to connect systems that not only run in different clouds potentially, but between on-prem and cloud. And we're working toward this goal of sometime later show this demo that Maxime wanted for years now, that you start from on-prem, you run your own cluster, then you migrate, let's say, to AWS namespace, then you migrate to GCP, then you migrate to Azure, and then you migrate back to your on-prem. So that's no strings attached. You can move your workloads wherever you want because of part of the system. Another important consideration, I was talking about that this kind of replication trade-offs apply no matter where in the stack you use it. But if you try to do the same with kind of database level replication, I don't think it's even possible to achieve the same flexibility. Because the database only understands the records and tables. It doesn't have this notion of application level, what the meaning of that. It doesn't provide us this ability to send data, organize it in a way that makes sense for the system, for the application. And what's interesting, yesterday, it almost like Datadog folks, so some of my slides, they didn't, of course, but they arrived at the same conclusion that if they try to do database just another application, nothing would have worked. And then if you add like Elasticsearch in the picture, that's even worse. So we solve this problem, right, of migration. Is that enough? Like, have we solved the problems? And of course not, it's not the case. Let's say we have this replicated namespace, and we can fail over, but if our workers or starters run in one region and that region has an outage, that's not gonna help that namespace is available in that region. So for application design, you need to look at the whole picture, the bigger picture. And the more resilient solution is to run workers or starters in both regions. And this is a cost consideration. Like if it's relatively cheap, it's okay to run two sets. If they're expensive, that we might want to scale it down and dynamically scale up. But again, it depends on how critical it is for business. If we need to run nonstop or full capacity, that may be worth the money. If we can afford a few minutes to scale up workers in case of failover, that's fine. So that is a business choice. But sometimes it's even more complicated. You have your one or more namespaces, they have some kind of interrelations, and you have some external dependencies, like maybe that's a database, which may be replicated by itself. And actually, in our control plane in Temporal Cloud, we have exactly the setup. We have control plane database that we replicate between different regions. So it's not just a matter of failing over a single namespace. You need to look at application as a whole. There are other options. I keep repeating the same message. It's business requirement specific. Like if my application just processes a bunch of incoming inputs, like for example, I process social network posts, right, do some analysis, or maybe genome processing, I actually don't care if I execute part of the work in one namespace, part of the work in another namespace, and there is this pattern that some customers use, call it standby namespace or a disaster recovery namespace, where instead of replicating, I have two different namespaces, and if there is any kind of outage in one region, I can just start using the other namespace without any sort of data moving between them. There's totally a legitimate pattern. A variation of it is if instead of having the second namespace idle, I split my traffic, and let's say it's in 50-50 traffic. It's kind of active-active setup where not only it ensures that both sides work instead of failing over and discovering something is not configured properly. Like I can go from 2 to 3 to 5. Like if I run like 5 namespaces and each one has 20% of the traffic, if I lose one, it redistribute the load, it will be like going from 20 to 25. I need much of a headroom capacity. The downside of this approach is that the experience, like UI experience of looking at this namespace is completely disconnected. Like I have 2 namespaces, I have to look at 2 UIs, so there is no like continuity between them. So that's kind of the price I have to pay for that. But it's doable. It's not people do that. for things to be kind of fully like ready, reliable in this case, across multiple regions, you probably want to run a full mesh of workers where you have workers in all the same regions, and then talk not just to their local region, but to all others, so that everything, all the workers can execute any task from any namespace. Now, to try to summarize what I was trying to say here, I would say that reliability, you can look at it in a way kind of similar to how we look at scalability. You can scale up, so we can increase our reliability by going up, by getting more and more sophisticated system. And like back in the 90s, it would be like tandem nonstop that you run this very expensive machine with hot swap CPUs and whatnot. Today, you go in and the cloud provider get more and more expensive setup. But at some point, it's not enough. You need to kind of scale out, go like geo-distributed and go outside of confines of the single provider. And if you look at distributed database providers, they have exact same setup. They offer synchronous replication within the region and say, across regions, we provide asynchronous replication. I think only Google is trying to say with Spanner that they can do synchronous across region, but you know, Google always does things their own way. The other consideration is where to replicate. Is it database application level? And I hope I made the case, and I hope that Datadog's folks made the case the same, that the application level replication is much more flexible, resilient, powerful than lower level. Yes, of course, we can use lower level as well as a kind of complementary thing, but the main power is at the application level. Also consider that these distributed databases, if you use them for replication, they usually tie to a single cloud provider. If you use RDS, you're stuck with AWS. You cannot move your data to like Azure or GCP. Same with Cosmos DB. You can't just move outside of Azure with that. So not only they're less flexible, they also tie you up because of this kind of data gravity. They want you to be in their cloud. And we want you to be free. We want you to be moving anywhere you want. Synchronous versus synchronous replication is really CP versus AP decision. And back a few years ago, we discussed, I kind of brought this question, or the kind of engineering discussion, should we build synchronous replication? Should we support that? And at the time, we decided that our customers really need asynchronous. They need availability because it's most important for business to continue to run. And occasional inconsistency, if let's say some workflows got into some weird state, usually it's much easier for them to deal with that while the business keeps moving because of this kind of partition state of the application. And so we chose to build asynchronous, and it was already kind of supported by the stack. But it doesn't mean we will not introduce it at some point later. We may decide, okay, this is also an option. You go to UI and say, I want a replicate namespace, but I want it to be synchronous. We have not heard these asks yet. So that's why we're still on asynchronous application, and probably will be for a long time. Temporal programming model is kind of like hand in glove for replication. It was designed this way. Of course, it's not a coincidence that it happened. It was designed with this kind of event sourcing model in place, and it has these benefits of determinism requirement, that it's much stronger eventual consistent than usually see otherwise. And the last point is that when we build application system, we need to look at the whole like big picture. We can't just make one single component reliable because you're as reliable as your weakest link. You need to look at the big picture and look at how to make reliable every single piece of the component in the stack. And that's all I had for you for today. Thank you very much. Any questions?
All right. So we got time for probably 2 questions, I'm going to guess. If you have a question, go ahead and raise your hand, and I will jog over to you in an Oprah-like fashion. Anyone? That's Donahue, not Oprah. Oprah used to sit in a chair. I don't know what I'm doing. It's morning. No questions. So that's fantastic. Well, okay, I have a question. So when you were, you sat down at one point when you're designing Temporal, and you're saying, you said you ultimately decided an asynchronous replication because you wanted to prioritize availability over consistency. Mm-hmm. and you touched on that, like some of the benefits of that, but like, why did you really focus on that? What was the key thing about either our customer base or your previous experience that caused you to prioritize the A in CAP over the C?
Oh, well, look at kind of typical applications. You're processing, say, a bunch of financial transactions. Like, let's say you have, 10,000 transactions. And let's say 2 of them got into some kind of weird state. What would you prefer? Stop the business for these 2, or you want to process another 10,000, and just investigate and fix them if that happens? And it's all probabilistic. It's not like it will happen every day. It may happen like once a year. And so like talking with customers, we see that they prefer business needs to keep going. Don't stop my business because of like some perfection.
What would be an example of a use case where you would want a C over an A?
So scenarios where latency is less critical. Like for example, infrastructure management. I'm setting up my cluster, right? I don't have any traffic on it. I'm just deploying nodes, like Kubernetes, software. It's okay for me to block. Like it's not on a critical path. I'm not processing any traffic. And it's much simpler when it's consistent. The worst case, I can restart it. So it's a very different, nobody's waiting, the customer waiting for this cluster to be finished. So strong consistency may be a better option there.
Thank you, that's excellent. All right, one more last call for questions. Yes. Get some cardio in this morning. Sorry, where was the hand?
Not a really precise question because I'm not still enough familiar with the determinism issue. But my understanding is that when you do the replaying of the log of events, if you have a different version of the workflow, you may have a mismatch between what you expect to find and what is actually recorded, right? And if when you have such cases, there's no other possibility than just throwing the error and classifying this as something that needs to be, as you said now, investigated and try to start again for the others. Is it the correct view?
There are 2 different things I would say there. So one is determinism of execution. For example, what the model doesn't allow to do is to like generate UID or take a timestamp in a kind of normal way. So you need to do it through a wrapper that will do it once, generate UID and record it in the database. So that we can replay how the times will be exact same UID, you will not regenerate a new one. Or like the timestamp, it will be captured the first time you ask for it. So that's kind of some determinism rules. With versioning, it's slightly different. If you change code logic, if you had like a switch statement with 2 options, now you have 3, and you go to the 3rd branch that wasn't there, or you removed one. And then when replay happens, it gets into the situation that is the event that is not there. And so the code versioning, there's multiple ways. There's patch API, and there's support for just running workers of different versions and attaching the right worker based on the version when the workflow was started. This is more like for logic change, as opposed to like side effects that you want to capture and not violate the side effects. Did I answer?
All right, one last one, we're going to squeeze it.
Just a quick question on eventual consistency. So we're using Temporal Cloud, and do you have any kind of targets with, for time windows for that at all, or?
Good question about target. So we have a metric for replication lag, and you can watch it for replicated namespaces, and it's sub-second. It's within milliseconds usually, like 100 millisecond, 200 millisecond. But I think one other thing what's important to keep in mind is most of the outages we see, pretty much all we've seen, they're not like region is down. They're more like brownouts. So some latency went up and want to failover. And so in these brownouts, we can have clean failover so that all data, it will not be inconsistent. Like when we failover, all the data will be there. And that's the majority of the cases because it's a brownout. It's not a complete like cut of connectivity, which statistically will happen at some probability, but we've not seen that at all. So kind of that's why it's still much stronger than eventual in reality.